Hi guys, welcome to the next section, using recurrent neural networks for predictive analytics. Now, we move on to the first video of this section that deals with using BRNN for image classification. Let's look at contextual information and the architecture of RNNs. Human beings don't start thinking from scratch. The human mind has the so-called persistence of memory, the ability to associate the past with recent information. Traditional neural networks instead ignore past events. Taking as an example a movie scene's classifier, it's not possible for a neural network to use past scene to classify current ones. RNNs were developed to try to solve this problem. In contrast to conventional neural networks, RNNs are networks with a loop that allows the information to be persistent. An RNN is different from a traditional neural network because it introduces a transition weight W to transfer information between times. RNNs process a sequential input one at a time, updating a kind of vector state that contains information about all past elements of the sequence. Now, let's see some commonly used architectures of RNNs, such as LSTM, BRNN, and GRU. BRNNs are based on the idea that the output at time t may depend on the previous and future elements in the sequence. To realize this, the output of two RNNs must be mixed. One executes the process in a direction, and the second runs the process in the opposite direction. This diagram shows the basic difference between a regular RNN and a BRNN. A more explicit BRNN architecture can be found in the figure where the temporal shared weights W2, W3, W4, and W5 must be learned in addition to W1 and W6. The unrolled architecture is also a very common implementation of a BRNN. This is the diagram of unrolled architecture of a BRNN. The network splits neurons of a regular RNN into two directions, one for positive time direction and another for negative time direction. With this structure, the output layer can get information from the past and future states. Now, we will move to using BRNN for image classification. Let's see how to implement a BRNN implementation example using the TensorFlow library. This example is using the MNIST database of handwriting. We will begin importing the libraries. Notice that RNN and RNN cell are TensorFlow libraries. The network will classify the MNIST images, so we have to load them. We define the learning parameters. To classify images using a BRNN, we consider every image row as a sequence of pixels. Because an MNIST image's shape is 28 into 28 px, we will then handle 28 sequences of 28 steps for every sample. Now, we configure the network's parameters. We define the data MNIST input, time steps, number of hidden layers, and total MNIST classes. Next, we set up the placeholders, which we use to feed to our network. First, we define a placeholder variable for the input images. This allows us to change the images that are input to the TensorFlow graph. The data type is set to float, and the tensor's shape is set to num input. None stands for a tensor that may hold an arbitrary number of images. Then we fix a second placeholder variable for the labels associated with the images, which were input in the placeholder variable x. The shape of this placeholder variable is set to num classes, which means that it may hold an arbitrary number of labels, and each label is a vector of length num classes, which is 10 in this case. The first variable that must be optimized is weights, and it is defined here as a TensorFlow variable that must be initialized with random uniform values, and whose shape is 2 into number of hidden number of classes. Here's the weights definition. Then we define the corresponding biases. With the following BRNN function, we define the weights and network biases. To achieve this purpose, we apply a sequence of TensorFlow transformations using these lines of code. Unlike in the previous model, we define two types of LSTM cell, a forward cell and a backward cell. Then we build the bidirectional network using the imported class RNN.staticBidirectionalRNN. Similarly to the undirectional case, RNN.bidirectionalRNN takes an input, and builds independent forward and backward RNNs with the final forward and backward output's depth concatenated. The input size of forward and backward cells must match. The BRNN returns an output tensor for determining which of the 10 classes the input image belongs to. The value returned by BRNN will then be passed to the pred tensor. We have to compute the cross-entropy value for each classified image because we must have a measure of how well the model works individually on each image. Using the cross-entropy to guide the network's optimization procedure, we need a single scalar value, so we simply take the cross-entropy average evaluated for all the classified images. The obtained cost measure will be minimized by an optimizer. We use the atom optimizer, which is an advanced form of atom optimizer. We add performance measures to be able to display progress during the training phase. It is a vector of booleans where the predicted class equals the true class of each image. The correct pred is used here to compute the classification accuracy by first typecasting the vector of booleans to floats so that false becomes 0 and true becomes 1, and then calculating the average of these numbers. All the variables must be initialized before we start optimizing them. Now, we will define 3 separate lists that holds the training loss and training accuracy. We then create a session that will execute the graph. During the session, we get a batch of training examples. Batch_x now holds a subset of training images, and batch_y is a subset of true labels for those images. We put the batch sets into a feed_dict with the proper names for the placeholder variables. Then we run the optimizer through ses.run. We calculate the accuracy and the loss values on these sets. Also, we save the mini batch loss, training accuracy, and step information. At the end of the training session, we get a batch of testing examples. Finally, we calculate and display the accuracy on this test set. We show only an excerpt of the output. Here, we visualize the loss value and the accuracy evaluated on the batch sets. It will take some time. Now, let's see the training error and accuracy per iteration from the graph. From the graph, it is clear that the training loss decreased over 2,000 iterations and slightly increased over 4,000 iterations and was stable after 600 iterations. Now let's plot accuracy over time. From this graph, it is clear that the training accuracy increased to about 100% and had hit a plateau by 1,000 iterations.